What is software quality? It sounds simple, but it's not. On one hand, software quality is hard to define and even harder to measure. On the other hand, we all know the consequences of poor quality: costly bugs, system failures, frustrated users, and of course, damaged reputation. I created this playlist to give you a solid foundation in the main concepts of software quality, using examples from automotive software development. In this first video, I'll introduce the core concepts of software quality. We'll cover the definition of software quality, the differences between stakeholder needs and stakeholder requirements, the V model, the difference between process quality, product quality, and quality in use. Finally, we'll take an overall look at the characteristics of good quality software. This is an important video that will set the foundation for our journey into software quality. In the following videos, I'll explain each quality characteristic in detail and provide practical examples and metrics. Don't worry if you are a beginner, I'll explain everything step by step in a simple and practical way. By watching this playlist, you will learn how to identify the quality characteristics of your product, define requirements and metrics to measure them, and to discuss software quality confidently with other professionals. I'm Giuseppe. I'm a principal assessor and instructor in Automotive Spice. I evaluate automotive software quality through formal assessments, but I also help suppliers and car makers improve their software processes and quality. Every day I see real-world consequences of poor software quality: costly rework, last-minute firefighting, delays in product launches, and of course frustrated teams trying to fix issues under pressure. These experiences show just how important quality is. On this channel, I share the knowledge I've gained from years of working in software quality, practical insights, examples, and best practices you can apply in your own projects. If you want to understand software quality and learn how to apply it successfully, subscribe to this channel. Let's get started. When we talk about software quality, the first thing that we have to consider is that quality often means different things to different people. Everyone involved in the software development views quality from their own perspective. For example, from a developer on the supplier side, quality means clean, well-structured and maintainable code. For a tester, it's about finding and fixing as much bugs as possible. For a project manager, it's meeting requirements, following standards and delivering on time. For car makers, good software is easy to integrate, reliable under all conditions, and it's safe, secure and maintainable. For drivers, quality is all about trust. They expect software that's intuitive, responsive and reliable, whether it's voice commands, touch screens or safety critical systems like braking or autonomous driving. The expectation is simple: it works, it is safe and secure. For regulators, quality means safety, security and compliance, protecting people, vehicles and the environment. Different groups care about different aspects of quality. These groups, suppliers, car makers, users, regulators, etc., are called stakeholders. Now, if a project team doesn't define what quality means for each involved stakeholder, every member may move in a different direction. And without a shared understanding, teams often make shortcuts or make decisions that create long-term problems. Shortcuts are a source of quality problems. For example, over time the software becomes harder to maintain, to extend or debug, and the team builds technical debt. Technical debt slows down future development because every new change takes more effort and introduces new risks. As a result, the code becomes fragile, innovation slows, and fixing issues costs much more than doing things right from the start. That brings us back to the key question: what is software quality? The answer comes from the ISO 25010 standard. This international standard was created to give developers, managers and their organizations a common language for evaluating quality across different industries. Basically, the standard says that the quality of software is the degree to which the software satisfies the stated and implied needs of its various stakeholders. In simple words, software quality is not just about writing great code or delivering on time. It's about meeting stakeholders' needs, fulfilling expectations, and creating real value through the software. The definition of software quality introduces two key ideas: stated and implied needs of stakeholders. Let's break this down. Stated needs are clearly expressed or documented like requirements written in a specification. Implied needs are not directly stated, but they are expected as obvious. For example, the car shall not explode when I start it. But there is also a third type, unaware needs. These are needs stakeholders don't even realize they to have, often because they lack on technical knowledge. For example, a driver might not think about cybersecurity, but still expects the car to protect their personal data and preventing hacking. Needs and expectations alone are not enough to drive development. They can be incomplete, inconsistent, or even contradictory, like wanting a system that is both extremely fast and extremely secure, which might not be possible within the same cost or time. That's why the first step in developing a software-based product is to collect all stakeholder needs. Let's make an example of a stakeholder need. The driver wants the headlights to turn on automatically when it gets dark. This is a need as it expresses what the driver wants, but it's not measurable or detailed enough for developing or testing. The next step is to turn a stakeholder's needs and expectations into stakeholder requirements. In engineering terms, this is the first step of requirement engineering. Stakeholder requirements are formal statements that explain what the system must do to meet stakeholders' needs. Stakeholder requirements must be documented, analyzed, and communicated to affected stakeholders and parties. These requirements then guide the development process. In the previous example of headlights, we can derive the following stakeholder requirements. Please note, this list is incomplete, but it gives you an idea of how functional requirements, performance requirements, safety requirements, and usability requirements might look like. These requirements are input to the software development process. In this playlist, when I talk about software development, I'll use the V model as a reference. The V model is a framework used in software engineering that links development phases on the left to testing and verification phases on the right. There are different phases like requirements analysis, software architecture, detail design, code, etc. that are logically connected with each other. Each phase on the left has a corresponding phase on the right. Here's how it works step by step. Software requirements analysis. This is a starting point. Stakeholders' needs and expectations are collected, analyzed, and formalized into software requirements. These requirements define what the software must do. The software architecture is derived from the software requirements and defines the software overall structure, the components, and how they interact. Each component from the software architecture is further detailed into the low-level design. This includes class diagrams, algorithms, data structure, and detailed specification needed for coding. In the implementation phase, developers write the actual code based on low-level design. The software is built from the bottom according to the plan. In the unit test phase, each software unit is tested individually to verify it works according to the detailed design. In the integration test phase, components are integrated and tested together to ensure they work correctly with each other and according to the software architecture. Finally, we have software testing. The complete software is tested against the software requirements to ensure that all requirements are met. The key idea of the V model is that each development step is derived from the previous one, and each testing step is directly linked to a development step. This ensures traceability, reduces errors, and makes it easier to detect problems early. And remember, if requirements are wrong or incomplete, the whole system will fail to meet stakeholders' expectations. Having effective processes in place is essential to ensure that stakeholder requirements are transformed into high-quality products. Here are the key takeaways so far. Stakeholders' needs and expectations can be stated, implied, and unaware. Stakeholder requirements are derived from stakeholders' needs and expectations. Stakeholder requirements must be documented, analyzed, and communicated. Effective processes enable skilled engineers to perform at their best and transform stakeholder requirements into high-quality products. Now let's continue with software quality and introduce the important concepts of product quality and quality in use. Now imagine you are a supplier of an electronic control unit like our automatic headlight control system. You deliver your ECU to a car maker. They integrate it with all the other components and deliver a finished car to the end users. Software quality can be divided into two main areas: product quality and quality in use. Product quality is about how good the software itself is, regardless of who uses or how it's used. Quality in use is about how well the software meets the user's needs in the real world. That is, the software meets the stakeholders' needs and expectations. Think of this in this way. Even if the software is well written and fulfills its requirements, it must still be useful and effective for the end users. For example, if not all requirements are captured, the product may fail to meet the user's needs. Let's come back now to the automatic headlight control system as an example. The software is developed according to all requirements that we have considered. From a product quality point of view, the software is great. It's functionally correct, reliable, and maintainable. But now let's look at what happens in real driving conditions. Imagine the system turns on the headlights every time the car passes under a short bridge or a line of tall trees, because the light briefly drops below the threshold. The driver finds the headlights constantly switching on and off during normal daylight driving. From the driver's perspective, this is annoying, distracting, and confusing. It reduces the driver's trust in the system, and it may even cause drivers to think something is wrong with the car. Even though the software technically meets all the product requirements, it fails to deliver good user experience. Most likely, some specific stakeholder requirements were not properly defined or considered in this example. These problems often arise from weak development processes, especially in requirements engineering. In this example, even with good product quality, the result is poor quality in use. In general, we can say that good product quality is a precondition for good quality in use. That means it is a necessary condition, but it's not sufficient to ensure quality in use. If product quality is low, quality in use suffers. Now let's understand this point better. Let's deep dive into the concept of product quality. This can be divided into two parts: internal quality and external quality. Internal quality is about how the software is written, structured, and maintained. This is a white box, static view of the software. In our example, the software is well structured with separate modules for ambient light sensing, GPS, tunnel detection, and headlight control. The code is clean, well documented, and easy to maintain so that engineers can quickly fix bugs or add new features. Unit tests cover all modules, and integration tests ensure components work together reliably. The result? High internal quality. The software is robust, maintainable, and ready for future updates. External quality is about the behavior of the software that can be observed externally from a black box perspective. For example, the headlights switch on and off exactly at defined thresholds, the tunnel detection works as expected, the reaction times of 2 seconds are met, the software meets all requirements. The result is good product quality. Of course, internal quality affects the behavior of the software, external quality, and this has an impact on quality in use. Let's make an example. The headlight software has internal quality problems, like for example spaghetti code, the light sensor, GPS, and headlight control are tightly coupled in one big module, no software architecture or detail design, lack of documentation, engineers cannot quickly understand or modify the code, minimal unit or integration testing, bugs are not found early, hard-coded thresholds, lux values and tunnel detection parameters are fixed and scattered into multiple places. The result is the software is hard to maintain, error-prone, and difficult to update. Internal quality is compromised. External quality and quality in use suffer. The impact on external quality is that the system occasionally misreads ambient light or tunnel conditions because of tightly coupled modules conflicts. The impact on quality in use is that the driver experiences headlights turn on and off unpredictably, sometimes during bright daylight or inside tunnels. The key takeaway here is poor internal quality directly compromises both product quality and quality in use. The question here is, what can we do to ensure good internal quality and good external quality? This brings us to the next key point of this video, process quality. Process quality is about how well the steps and procedures to develop software are defined and followed. In simple terms, it's doing the right things to the right way, from collecting all requirements, building a solid architecture, creating detailed designs, writing quality code, and of course, testing everything. Why it's so important? Even skilled developers can make mistakes if processes are weak. Poor processes can lead to bugs, inconsistencies, delays, and expensive reworks. Strong processes, on the other hand, reduce errors, save time, and make sure the whole team works smoothly toward the same goals. Good processes help great engineers to do their best work. Process quality directly affects product quality. When processes are well defined and followed, stakeholder requirements are captured, implemented, and verified properly. The result is software is reliable, maintainable, and meets expectations. Process quality also impacts quality in use, how the end user experiences the software. Poor processes can lead to slow, buggy, or frustrating software. Good processes increase the probability that the software is intuitive, dependable, and provides real value to the users. In automotive software development, software quality can be formally evaluated using automotive spice. Automotive spice is a model that assesses how well an organization's software development processes are defined and implemented, helping ensure high-quality products and safer, more reliable vehicles. In short, the key takeaway is strong process quality lays the foundation for high product quality, which in turn enables excellent quality in use. Now let's introduce the concept of software quality characteristics. In automotive software development, Automotive Spice helps organizations define and implement high-quality software development processes. At the same time, standards like the ISO 25010 guide us on what characteristics the software itself should have in terms of product quality. This standard identifies the following 9 characteristics: functional suitability, performance efficiency, compatibility, interaction capability, reliability, security, maintainability, flexibility, and safety. The characteristics of the quality in use are defined in the ISO 25019 standard. These are beneficialness, freedom from risk, and acceptability. In the next videos, I'll deep dive into each of these characteristics, one by one, to really understand what they mean in practice and derive metrics for them. The key takeaways here are: Automotive Spice is the model that is used in automotive industry to achieve good quality processes. The standard ISO 25010 defines quality characteristics for product quality. The standard ISO 25019 defines quality characteristics for quality in use. Now, let's put all the pieces of the puzzle together. When you start developing a product, the first step is to decide which quality characteristics apply to your software for both product quality and quality in use. The ISO 25010 and the ISO 25019 might support you. From these characteristics, you derive stakeholder requirements for software quality. These requirements then guide your entire development process. The development process is Automotive Spice compliant and ensures that the final product truly meets stakeholder requirements, but also stakeholders' needs and expectations. In the next video, we'll go through the quality characteristics for product quality and quality in use. We'll deep dive into each characteristic, explore what it really means, and I'll share plenty of examples of requirements and metrics. Before we continue, just one request. If you find this video helpful, please give it a like and subscribe to my channel. It really helps me to create more high quality content that supports your career and improve your knowledge. Thank you so much.